Hi, everyone. Welcome to the online causal inference seminar. Today, we have a talk by Stijn Vansteelandt from Ghent University. We'll be talking about Assumptionlean causal modeling. After that, we will have a discussion by Betsy Ogburn from Johns Hopkins. And actually in the Q&A, we have Oliver Dukes, also from Ghent, answering questions. So feel free to submit as many questions as you'd like. Now I'll pass it off to Ying, who will describe how you can do that.
Thank you, Emma. So as usual, please submit your questions through the Q&A section. If you haven't used it before, it is just a button at the bottom of the Zoom window. So we encourage you to submit the questions as you have them. If it is a small clarification question, maybe I will raise it up to stay lively, and I will save larger questions for later as Stijn stops. So please do submit it through the Q&A for us to better track it and for it to be visible to other people. So without further ado, please take it over, Stijn.
Thank you. Does this look okay? Yep.
Yes.
Good. Well,
yes.
Thanks very much for the opportunity to present this work. Also, thanks to Oliver for being on the Q&A, and Torben Martinussen and Kelly van Lanker who've also joined this work with me. Okay, well, let me start with a little bit of the conceptual introduction and the motivation for the work that I'll talk about today. Over the past few decades, we've seen a very successful move towards prescriptive causal methods. So those methods where we evaluate the effects of specific interventions. The focus here is often on fairly simple estimands, model-free estimands, like the mean of a counterfactual Y1, as opposed to the modeling tradition where we focus on parameters in statistical models. And that, I believe, has led to really good progress. It leads to more informative answers to policy questions, and also gives us a way of obtaining valid data adaptive inference, even when machine learning becomes part of the game. Now, this prescriptive approach to causal inference, you could say, makes our thinking a bit more hygienic. And to make that point clear, if you just think about variable selection in a Cox regression model, later I'll talk about Cox regression in a bit more detail. Well, then, as we keep on adding variables to the model, we keep on changing the estimands. If suppose that we care about a hazard ratio that captures, say, a treatment effect coefficient. Well, then, as we keep on adding variables, we keep on changing the estimand. We keep on changing the ignorability and censoring assumptions under which we work. And no surprise that it's becoming really difficult to obtain valid post-selection inference. And that we can resolve by targeting a pre-specified estimand and working under pre-specified assumptions. That's basically why the focus on estimands gives us a way of resolving the problems with the more traditional modeling tradition. Now, I'll also give a bit of critique to this prescriptive approach to causality, and that is that by giving up on models to summarize patterns in the data, I think that the prescriptive approach to causality has largely limited itself to simple causal queries. And in particular, in an attempt to sort of align our data analysis to the settings that have been worked out in the literature, I believe that large compromises are sometimes made at the risk of abandonment of this hygienic thinking. To make that a little more clear, it's not uncommon to see that people dichotomize exposures more for mathematical convenience than to serve the scientific question. For instance, we might focus on what if all individuals in the study had above median versus below median inflammation markers. It's also not uncommon to end up asking overly ambitious questions like, what if everyone had a BMI of 25? What if all pregnant women smoke during pregnancy, which again may be a bit remote from the real world? And even questions that may seem simple, like what if all patients were always treated? may quickly end up being overly ambitious, because over time we may find that certain treatment options are not feasible for certain individuals. And then questions like this can end up being overly ambitious. And finally, as the analysis becomes more complicated, it's also common to fall back in the statistical model tradition, and giving up on that focus on a pre-specified estimand, but focusing instead on the usual model parameters, like in marginal structure models, in the target trial approach, in IV analysis. Now we can do better with the available causal methods. We can focus on the effect of a shift in the BMI distribution. If we believe that smoking is not a feasible option for all pregnant women, we could think about restricting the population of pregnant women in whom we evaluate the effect of smoking. We could focus on dynamic interventions, but all of that is easier said than done, especially because I think in many scientific studies where we seek to learn cause-effect relationships, no specific interventions may yet be envisaged. The prescriptive approach to causality, I think, can end up being artificial in those cases. What shift interventions should we focus on? Should we think about shifting the marginal distribution of BMI, the distribution conditional on certain subject characteristics, shifting to what distribution? I think these are difficult questions to answer when we cannot link the study to a clear pre-specified intervention. How should we restrict the study population to those pregnant women more likely to smoke? What dynamic intervention keeps us close enough to the real world? This is an issue that we've experienced in a recent Statistics and Medicine paper, where we looked at at basically optimal treatment strategies for critically ill patients with acute kidney injury, and where we had a particularly hard time finding interventions, dynamic interventions, that are close enough to what the data tell us, so that we're not really making strong extrapolations away from the real data. The point I want to make is that I think the prescriptive approach quickly becomes demanding, and often I think in need of expert statisticians to help choose proper estimands that are not too ambitious in what they try to get from the data. And also in view of the fact that analysis may quickly become difficult and may not have the stability that we would like to see for large-scale use. So there's two motivations for this work. The first one is I'm a bit concerned that the advancement in causal inference are restricted to perhaps a select few. And a first aim is to make them more widely accessible, even in those settings where we do not yet have specific interventions in mind, and hopefully without the dangers of asking overly ambitious questions. How will I do that? Well, in the talk, I'll focus on the simple case and the assumption that a collection of variables L suffices to adjust for confounding of the effect of exposure A on outcome Y. And at the moment, we're working on relaxing that assumption or working on the different assumptions, but this is the assumption I'll focus on during the talk. And so what I'll do to basically handle the concerns I just talked about, what I'll do is relate back to the descriptive approach to causality, which has a less ambitious aim to provide insight into the causal data generating mechanism. And I want to be clear, I don't view this as a substitute to the prescriptive approach to causality when we do have clear interventions in mind. I think this is the way to go, but I view it as hopefully a feasible strategy that is hopefully better accessible to non-statisticians, especially in those cases where we don't have specific interventions in mind. Now, this descriptive approach to causal inference makes use of models to summarize information in the data, and this modeling tradition has been severely critiqued, and rightly so. Now, many of the critiques apply equally to causal models like marginal structure models, partially linear models, and so forth. And therefore, the second motivation for this work is, even in settings where we would like to do prescriptive causal inference, to utilize causal models in a manner that avoids the typical critiques to the modeling tradition. Now, let me be a little more explicit about those critiques to the modeling tradition. I'll list a few. First one is what Breiman called Occam's dilemma, and that this is the fact that as a statistician, we may often feel a bit torn when we use statistical models in finding a model that is simple and interpretable and can be communicated to clinicians, for instance, as opposed to working with a correct model that describes the patterns in the data correctly, that does a correct confounding adjustment. And achieving that with one and the same model can be difficult. So these may be conflicting aims. The compromises that we make between keeping the model simple and interpretable versus correct lead to model misspecification and bias. Reliance on models may lead one to overstate precision and also obscure what we obtain when the model is wrong. And I'll expand on that point in just a moment. Model building algorithms, variable selection strategies, they aim to prevent misspecification, but at the same time, they then invalid standard inference because it's often tricky to acknowledge the uncertainty that those algorithms bring. And the final point I wish to raise is what Breiman called the multiplicity of good models, the fact that finding the data generating mechanism is often overly ambitious because there may be many models, many very different models that fit the data reasonably well. Let me expand a little bit on the point. What do we end up estimating when the model is wrong? Suppose that we use ordinary least squares in this linear regression. I regress outcome on an exposure A and covariates L. Well, then when the model is misspecified and when A is dichotomous, it's quite easy to show that the OLS estimator converges to the expression here, where the first component is a bit like a weighted average of treatment effects. So we take a mean difference in outcome between, say, the treated and untreated with the same covariates L, and then we have a weighting factor that involves the true propensity score, as well as this pi tilde, which is a population least squares projection of the exposure on the covariate data. And then the second term is making a contrast of those two, weighting by the mean outcome in the untreated. Now, the second component here is rather disturbing because it has nothing to do with the treatment effect. And in fact, the whole estimand is rather complicated. And the point I want to make is that even in the simple OLS setting, the estimand that we end up working with, which is the expression here, ends up being complicated. There's no guarantee that it captures the conditional association between Y and A given L, and it may in fact differ from zero when exposure and outcome are independent given L. Now, there have been more general attempts in nonlinear models, say, to understand where estimators converge to when the model is misspecified. Very much the same kind of steps I just went through, but the answer is often disappointing, and in fact even far more disappointing than what we just saw for ordinary least squares. The answer is often complicated. In Cox regression, for instance, as a statistician, we would often hope that we obtain some average log hazard ratio when, for instance, the proportional hazards assumption fails, but unfortunately, life is often not as simple as that. And same in most causal models, I think we likewise don't understand what we're getting when the model is wrong. And so the work I'll talk about today is trying to deal with that issue. Now, going back to the prescriptive approach to causality, I think we've long accepted that the starting point of a causal analysis should be the choice of an estimand. And mediation is one clear example of that. I think we've more or less refuted the product of coefficient method because it's a little bit the world upside down. We have an estimator, but may not know quite exactly what it's giving us in terms of indirect effect. And so a key point from the famous Robinson-Greenland paper is that we should first pin down what measure of indirect effect we want to work with, and only then we can think about identifying and estimating it. But we seem to forget this when models are involved. In that case, we often end up working with estimands, just like in the OLS example, estimands that are determined implicitly by the probability limits of the estimator that we end up working with. And we often have a fairly poor understanding of what that means. Now, more recently, there's quite some literature on so-called projection estimands, where, for instance, the mean of a counterfactual YA given covariate data V is projected onto a regression model as a way of drawing non-parametric inference, even in this model-based context. But also this literature, I think, has a few concerns that motivated the work. The estimands used in that literature are not always chosen in view of interpretation. And I think a clear contribution of the causal inference has been precisely to make sure that we look at estimands that have a good interpretability. Some of the estimands being considered could be like the maximizer of the expected log likelihood, which does not necessarily have a good or has a good interpretation. And further, when we make projections on parametric models, then we can run into the same issues as I discussed for ordinary least squares. And let me give you one example. Suppose we fit a marginal structure model like here, where A is the dichotomous exposure, V is a subset of covariates contained in the vector of confounders L. And suppose that we use weighted least squares with the stabilized weights to fit the model. Well, then you can likewise show that when the model is misspecified, the estimator of the treatment effect psi converges to the expression here, which looks very much to what we saw before, except we're now conditioning on V instead of L, and the pi tilde is now a least squares projection of that probability onto L. But again, the point I want to make is that in these causal models, when the model is misspecified, we often have no very good understanding of what we're getting in that case. So in a GRSSB discussion paper, Oliver and I therefore advocated a different approach. And the key point here is that when we use statistical models or causal models, then we view the starting point as basically coming up with a model-free estimand that we can associate with the target parameter, which may be trying to capture treatment effects. And the model-free estimand that we'll come up with, we hope to construct it in such a way that it's interpretable, and also that it summarizes the effect of interests. Unlike what we saw on the previous slide, the expression here is not quite a summary of the treatment effects, because even though the first component is about treatment effects, the second is not. And we basically try to fix that issue. So the key hope is that with the approach that I'll explain in a moment, at least we have a guarantee of understanding what is being estimated when the model is wrong. So let me go briefly through the steps of the proposal. So the first step will be to specify the degree of parsimony that we want to use by means of a model, which could be a generalized partially linear model. So here on the scale of the log link, I assume that the chance of success, say, is linear in the exposure, and I'm not going to specify how that relates to the covariate data. This model is basically chosen as a way of summarizing the data. I'll make that a bit more explicit in a moment. This is not a model that I'll assume to hold in the proposal, but it's basically a sort of template to indicate that what I want to communicate to the clinical investigator is like a log relative risk, say. Then next, we'll specify a model-free estimand, which reduces to psi if the model holds, but remains interpretable when the model is wrong. So you could think of a weighted average of log risk ratios. And then because the estimand is model-free, we can then develop non-parametric inference. In full freedom, I say, because we don't have to tie ourselves to this regression model here on the top of the slide. when drawing inference. And that means that valid inference can be obtained even when variable selection is part of the game or machine learning. Now, as I said, despite the fact that models can be misspecified, I do believe that a model like this is somehow useful because it gives us a way of summarizing the information in the data and perhaps oversimplifying it to a certain extent. But after all, I think this is also the task of a statistician to make the results, to give them the sufficient simplicity so that we can communicate to our non-statistical colleagues. As I said, I'm not going to assume the model to be correct. So if the model holds, then the approach I'll discuss will give root and consistent estimators of psi. But if the model does not hold, we'll still understand fairly well what we're getting. So let me give you an impression of what estimands we will work with. So forget about the model for a moment. And suppose that we could analyze each stratum L separately. Well, then what I could do to basically make sense of this coefficient psi of L is within stratum L, we could do a least squares regression of the log risk on the exposure, and the ordinary least squares coefficient would then look like the expression here. And I can view this as a model-free summary of the treatment effect in stratum L. If A is dichotomous, then this is just a log relative risk. But the summary, if you like, psi L is well-defined more generally, even if the exposure is continuous. And in fact, dealing with continuous exposures has been one of the motivations for this work. Of course, the data in a single stratum will be too sparse to obtain good results. And this is why in traditional statistics, we would often want to work with a model like this that assumes the treatment effect to be constant. I'll not make that assumption, but instead I will summarize the different values of psi L for the different covariate strata. And we've chosen to do that by taking weighted averages, where the weights will be the variance of the exposure given L. And the reason why we focus on this variance weighting is because it's upweighting those covariate strata where we see real information about the exposure effect, where at least we see some variability in the exposure. So if A is continuous, well, then we may sometimes hope to see constant variability in A. In that case, we just obtain a mean of these log relative risks, if you like, or a mean of these least squares projections. If A is dichotomous, well, then the weights would be the probability of being treated times the probability of being untreated. And so we're upweighting people with a fair chance of being both treated or untreated. And arguably, these may also be the type of people in whom we would like to learn about treatment effects. Of course, by using weights, we're sort of changing the study population, and therefore we would advise to report accordingly weighted summary statistics of the age and gender and so forth distribution, so that we have a good understanding of what people we're learning about. And some work in progress is that we're likewise looking not at taking weighted averages, but looking at measures of variability in those treatment effects, so that we can also learn about treatment effect heterogeneity. Now, this weighted average may likely not be the type of estimands that you would want to target if you had a clear intervention in mind. Then probably we would want to focus on the more typical causal effect estimands, where we look at questions like what if all were treated versus no one were treated. We may want to look at shift interventions and so forth. And in fact, in practice, when communicating results to a clinician, I would even interpret psi as if this model here were to hold, as like a log relative risk, if you like. My aim is just to make sure that if the model does not hold, that I have a good understanding of what we're still getting, which is then a weighted average of log relative risks, if you like. And it's not that I think this has been a bit of a confusion in the discussions on the GRSSB paper that we might view this as an estimand that is sort of more attractive than the typical causal effect estimands. This is not how I think we view this. It's more like we may want to do interpretation as in this model, but have the guarantee that if the model does not hold, that we still obtain something sensible, like a weighted average of log relative risks. And if you remember from the OLS setting, we do not even have closely that guarantee with more traditional methods. Let me just show you what we do with Cox regression, and then I'll pause for a moment to hear if there's any questions. So for Cox regression, we would start from the continuously stratified Cox model. So here on the scale of the log link, I would assume the hazard of the event at time t to be linear in the exposure, and then I'm not going to specify how the effect of time and covariates looks like. Let me just explain for binary exposures. So then we could summarize the effect in terms of a log cumulative hazard ratio. So we take a contrast of the cumulative hazard at each time t in each covariate stratum L in the treated versus untreated group. Let me call this psi of TNL. And that would just equal psi if the proportional hazards assumption holds. But it's still a measure of treatment effect if that assumption is violated. And of course, we're not going to report that measure for each time and each covariate stratum. We will rather look at some measure of central location, like the summary here, where again we use weighted averages across covariate strata, and then we weight uniformly across time. Again, a mean is only one aspect of these estimands. So at the moment we're investigating likewise how we can study variability in function of time or covariate strata. I'll explain in a moment how we do estimation, but let me first hear if there's any questions.
We don't have too many questions, just okay. One question just popped up. It asks, can this equally be applied to parametric and non-parametric models?
Yeah, so in a certain sense, you could say in parametric, I mean, I will usually start working from like a semi-parametric Cox model in sort of building up the reasoning in targeting a certain estimand, but in principle, the same proposal, like if we were to parameterize the effect of L, we would basically come to the same type of proposal. I only care about the effect of treatment, so I want to come up with a proposal that works regardless of how this part of the model looks like. When I discuss the estimation strategy in a bit more detail, you'll see that at some point we'll need to estimate this as well. For that, we could use either machine learning or parametric regression, perhaps along with variable selection. So that there'll be some flexibility in making this parametric if we believe that this is the way to go, or making it more non-parametric if that is what we believe we should do.
Thank you. Another question just popped up. Shenbo Xu asks, what is the estimator for the Assumptionlean conditional average treatment effect?
Yeah, that's a good point, and we haven't, I think, given that a lot of thought so far, but it's something we've wanted to do to make it a bit more general. All that we've done so far is look more at interactions. How can we be more like, suppose there's an interaction between A and L, but like a parametric interaction in terms of a product term, how can we estimate that interaction to learn about treatment effects heterogeneity, or to get a bit closer to conditional average treatment effects? An interesting next step could be to see what else can we do if we really want to focus on conditional average treatment effect itself, in perhaps a setting where we also focus on continuous exposures. That we haven't given all that much thought yet, but it's something we've planned to look into.
Thank you. We still have more questions pop up, but for the interest of time, maybe we can continue and save them for later. Thank you.
Thank you. All right, well, let me give you an impression of how estimation works. Well, we have a model-free estimand, and the good news is that we can then estimate it also in a model-free way without tying ourselves to the more parametric model, like the generalized partially linear model that I started with. We don't have to tie ourselves to it, so we don't have to worry about model complexity. It's tempting to say, well, let's sort of make an empirical analog of the expression here. Instead of population expectations, we could take sample averages, this covariance, which is conditional on L. We could learn by taking residuals from the exposure and then multiplying by the link function G evaluated at the mean outcome. And perhaps we could use machine learning to get the mean of A given L and the mean of Y given A and L. That seems tempting to do, but unfortunately, it's a bad idea. This plugin estimator is generally biased, and it's also not so clear, especially if we start using machine learning for the mean of A or the mean of Y. It's not so clear what the uncertainty in those predictions would be and how that propagates into the estimator. And that makes standard errors difficult to obtain. Even the bootstrap is not a valid option in that case. So for this, to remedy this, we relate to the very popular developments on targeted or debiased machine learning, which I think are becoming very dominant in the field. And so what we'll do is we'll calculate the estimand's efficient inference function under the non-parametric model, and then obtain an estimator by setting the sample average of that inference function to 0. And that leads to a closed form estimator. And that's because we relate to least squares projections. So here you can see for the generalized linear model analysis how the estimator would look like. So we get the residuals in the exposure and then multiplied by this function mu, which involves residuals from the outcome, multiplied by the derivative, the first order derivative of the link function evaluated at the mean outcome. And then we also have a residual for the mean outcome on the scale of the link function. In practice, we would substitute all of the unknowns, like the mean of A given L and the mean of Y given A and L, and then this expectation given L. We would substitute those by estimates that we could obtain by fitting flexible parametric models, perhaps with variable selection, or using machine learning strategies. For Cox regression of a sensor time to event endpoint, if we make the assumption that the time to censoring is independent of the time to the event given A and L, well, then we find the efficient influence function to be the expression here, which involves quite similar terms, the log of the cumulative hazard. This function Q, which somehow dropped off the slide. So this is the mean of this log cumulative hazards given L. And then we have martingales and the survival probabilities for censoring and for the time to event. Those are the unknown nuisance parameters that we need to estimate from data. And we could perhaps, and that's what I'll do later, we could use random forest regression to give estimates for these survival probabilities, and therefore also for the cumulative hazard. We could use superlearner, for instance, to give us estimates of the mean of A given L. Importantly, all of these analyses do not involve inverse weighting by the density of the exposure given L, and this has been somewhat of an aim. In fact, in constructing estimands, we've aimed to focus on those that do not require inverse weighting by the exposure density, as this could quickly lead to instabilities in the analysis. Again, the point is that we can find an estimator for psi by setting the sample average of this expression to 0, and then solving for psi, and that gives the closed form estimation. So according to the typical theory on debiased machine learning, when sample splitting is used, that means if we estimate the nuisance parameters on a different part of the data than where we evaluate the estimator itself for the treatment effect. Well, then, if we do that, and moreover, the estimated nuisance parameters converge at faster than n to the quarter rates, then the variance of the estimator can be obtained as 1 over n times the sample variance of these influence functions, as if the nuisance parameters were given. And this is very much the strength of these methods, that even if we use complex methods like machine learning or variable selection, that we can still obtain valid standard errors, at least if those if this n to the quarter rate guarantee is attained. I'll give an impression from how this is doing in simulations. So the first simulation study looks at variable selection. So here I'm just fitting a standard Cox model for the outcome for the time to events. But you may remember that we also need models for the exposure, and for that I use superlearner, so a stacked learner involving a main effects linear model. So this is looking at a continuous exposure. Variable selection is part of the game. We also look at linear additive models and random forest regression. So we basically use a combination of these strategies. At sample sizes 200 and 400, you can see the a naive plugin estimator, which is not relying on the efficient influence function, but a bit along the lines as sketched before. In fact, here, the plugin estimator amounts to doing post-lasso, so using a lasso-based variable selection and then refitting the Cox model with the selected variables. And that gives a lot of bias, as you can see. It gives standard errors that are not at all in line with the real standard deviation of the estimator, because this is ignoring the uncertainty in the variable selection, and thus it leads to poor coverage. Same at the larger sample size. And then here CML for causal machine learning is removing that bias to quite a great extent, and giving standard errors more or less in line with the real standard deviation. This version is without sample splitting, and here we have a cross-fitting version with 5 folds, where we split the data in 5 folds. Each time use 4 out of the 5 folds to train the machine learning, and the remaining folds to evaluate the treatment effect. That typically leads to a bit more bias, but better standard error, a bit more precision, usually, and better coverage is what we've typically seen. This is a more challenging simulation study where you can see, so I'm looking at a 10-dimensional covariate vector L, but now we have fairly complex relations between the covariates and the exposure, as well as between covariates and the endpoint and censoring. And so here we use survival random forests for the survival probabilities and the cumulative hazards. And then again, superlearner for the regression of A on L, as well as the regression of the survival probabilities on L. And this is at sample size 500. It's a bit more challenging setting. Again, plugin estimators come with a lot of bias, and we can remove that to a fairly large extent with the proposed method. Not entirely. In fact, the cross-fitting introduces a bit of bias as well, but gives much better efficiency and standard errors more in line with the real standard deviation, but not yet up to speed in terms of coverage if we use cross-fitting here. So arguably larger sample sizes would be needed to make that happen. We seem to do well without cross-fitting, but likely in larger samples, the cross-fitting based estimator will take over. All right, so let me end with a brief discussion that lists the features of this proposal. We've aimed for this proposal to have the same flexibility as standard regressions. In particular, it can readily handle continuous exposures. It overcomes Occam's dilemma because we have one model only aimed to summarize the patterns in the data, which could be overly simplistic. But the real modeling to handle the curse of dimensionality happens behind, or happens in the background, if you like, via machine learning. And that hopefully prevents model misspecification bias. By being non-parametric in our inference, we avoid extracting information from modeling assumption. We obtain valid inference despite the use of machine learning or variable selection, at least if we attain the n to the quarter rates. The analysis can be nearly pre-specified, which is also very much the case for other device machine learning methods. And it's fairly simple to obtain because we've obtained closed form estimators. Let me draw a connection to partially linear regression. So one advantage I would say of this proposal is that it makes semi-parametric regression in partially linear models fairly straightforward, no matter the choice of link. And in other work on partially linear models, I think there have been difficulties, computational difficulties when handling nonlinear link functions or when handling high-dimensional covariates, difficulties in solving the required estimating equations. One advantage of other approaches on partially linear regression is that rate double robustness can sometimes be attained in at least in certain partially linear models, and Eric Chutkin has a lot of work on that. And rate double robustness is not attained in our proposal. What do I mean by rate double robustness? Well, in some of these partially linear model analysis, the estimator of the mean outcome in the untreated is allowed to converge slower than n to the quarter rate, so long as this is compensated by faster convergence of the propensity score. We don't have that guarantee in our proposal. However, this rate double robustness comes with a price. It's only attained if the partially linear model holds. And in fact, when the model does not hold, then these approaches do not even attain valid inference. It's likewise generally unclear where the estimator then converges to. And this is from one small simulation in the paper where we verified that G-estimators, at least data adaptive G-estimators, that the sandwich standard errors that we obtain for them are biased when the model is misspecified. Maybe a final point. So we're trying to achieve simplicity in the proposal by focusing on least squares projection, and that comes at the expense of some efficiency loss. So a bit of a question, and what has been a bit of a challenge in this work is to come up with estimands that retain good interpretability, that have the flexibility in handling continuous exposures, that have a reasonably favorable efficiency bound, and also that lead to efficient inference functions whose nuisance parameters do not depend on the unknown parameter of interest. We're doing some work on seeing, can we obtain estimands that are still interpretable but have more favorable efficiency, and I think we're making some progress there. In the context of nonlinear models, we see quite big improvements. I'll maybe skip this and point to some references. So the work I talked about today is mainly described in this discussion paper in GRSSB, and there's a more recent JASA paper on the Cox regression model. Thank you very much, and I look very much forward to the discussion.
Thank you, Stijn. So Oliver has actually done a great job answering a bunch of questions in the Q&A. So maybe we move on to the discussion right away, and then we'll see if we can discuss some more questions after that.
Yep.
It looks like I can't share my screen, and oh, there we go.
Yeah.
Okay, so thanks so much to Stijn for the excellent talk, and to Stijn, Oliver, Torben, and Kelly for the wonderful papers. And thank you to the organizers for giving me the chance to discuss this work. I really want to congratulate Stijn and collaborators on this really important work that I think could be potentially paradigm shifting in terms of how we think about estimating causal effects when well-defined, easily estimable causal effects are not, of obvious primary interest. In some ways, this is a very easy presentation to discuss because one of the papers was a JRSSB discussion paper. So there are 40-some pages of really insightful, diverse comments published in JRSSB, and I'd urge you to read through them if you're interested, because I can't begin to do them justice here. But a common theme among some of the more skeptical comments was what Stijn calls hygienic causal inference loses sight of some of the principles of prescriptive causal inference. So here's my view of an optimal causal inference workflow in the prescriptive vein. The first step is to define the causal estimands of interest, and we define them in terms of the full data, meaning the potential outcomes and possibly observed data as well, but without reference at first to any assumptions or models. These will be invoked later. And the point of isolating the definition of the estimand of interest from practical concerns about assumptions and models is that it avoids retrofitting the question to match your preferred methods. The second step is to propose a set of assumptions that can be justified either by existing research or domain expertise, or in the absence of that are mathematically as unrestrictive as possible. The third step is to communicate these assumptions transparently and to offer intuition for any technical assumptions, to explain how a practitioner or user of the analysis could reason about when assumptions hold or when they're violated. And then the fourth step is to deduce whether and how the observed data, so the projection of the full data onto the observable random variables, whether and how the observed data identifies or maybe partially identifies the causal estimand given the assumptions. The points of steps 2, 3, and 4 here, so proposing, justifying, and communicating, identifying assumptions, is to again guard against reflexively fitting a parametric model and interpreting the parameter of interest as a causal effect. And prescriptive causal inference tends to be very skeptical of using parametric models as identifying assumptions because, and Stijn pointed this out, misspecified models can lead to really faulty, uninterpretable conclusions. Only in step 5 do we get to actually using the data. So in step 5, we estimate or otherwise use the data to learn about, so for example, by driving bounds on the observed data estimand that identifies our causal estimand. And here we try to use only justifiable or as unrestrictive a model as possible. So at this stage, prescriptive causal inference tends to prefer non-parametric estimation methods, but I think Stijn rightfully points out that often, for example, if the treatment is continuous, low dimensional summaries are really necessary at this step, and the choice among those low dimensional summaries is often ad hoc in practice. And now the 6th step is to assess the robustness of any conclusions that you derive from step 5, from estimating the causal effect. Assess the robustness of these conclusions to violations of both causal and modeling assumptions. And a lot of research in causal inference is around these robustness checks and other ways to ensure that you don't draw conclusions beyond what the data and justifiable assumptions license. Contrast this with the kind of skeleton workflow that Stijn proposed, and I'm really using this as a straw man. It's not that Stijn suggested that there shouldn't be additional steps here, just that these are the core steps in his proposal. It's a really pared down workflow where you identify the question of interest, so you specify the effect of A on Y controlling for confounding by L, and then you estimate the weighted average of L specific covariances between A and Y. And what's missing from this workflow is attention to the identifying assumptions, to the interpretation of the effect that's estimated in step 2, and to assessing the robustness of the estimation procedure to identifying assumptions. The brilliance of this workflow is that there's very little to be done in terms of assessing robustness to modeling assumptions, at least not in the same way we typically would, because essentially no modeling assumptions are invoked here. But I'm going to propose a kind of hybrid of these two workflows, and I think this goes a long way to address a lot of the skepticism expressed by prescriptive causal modelers like myself. And I just want to reiterate that a lot of these steps are in fact endorsed by Stijn and his co-authors in their papers. It's just that they're not part of the kind of core presentation of the novel ideas. So the first step would be, again, to identify the question of interest, but this time specify only that we're interested in the effect of A on Y. Then we use kind of the types of thinking that are used in prescriptive causal workflows to assess the assumptions under which covariates L would suffice to control for confounding for the effect of A on Y. So you would bring in subject matter expertise, prior research, reasoning using DAGs or other graphical models, etc. Then the third step would be to communicate these assumptions really transparently, and especially to communicate the ways in which they might be violated. So if there's any uncertainty about whether L suffices to control for confounding, or about whether L might include instruments or colliders, that would be, something that would put forth in the most transparent way possible. Step 4 is to look for evidence of non-monotonic AY associations and for evidence of qualitative AL interactions. And that's because if the association or the relationship between A and Y is U-shaped, for example, then the linear slope of Y on A can be very misleading. And this is all modulo the link function G. Similarly, if the direction of the AY relationship can change across values of L, then taking a weighted average across levels of L can be misleading. And I'll come back to this on the next slide, but for now, I would just recommend proceeding with extreme caution if there's any substantive reason or reasons based on exploratory analyses to think that effects might not all go in the same direction. Now, step 5 is to estimate Stijns estimands. And then finally, step 6 is the same as in the standard prescriptive causal workflow where we perform sensitivity analyses. So I think the most important sensitivity analyses to perform here are for unmeasured confounding. This is a type of analysis that's very well established for traditional causal estimands and can easily be used here. But it's also the case that when machine learning is used to estimate the conditional expectations of A and Y, I think it's important to realize that the quarter root N rates may not be as achievable as we would like to think. And so I'll just point to, the need to think more about this. And Liu, Mukherjee, and Robbins have proposed a test that can reject the coverage of intervals derived from machine learning procedures like the one that Stijn proposed, and it essentially tests that standard errors dominate bias, which is a necessary condition for good asymptotic approximations. And I'd love to see this kind of sensitivity analysis extended to Stijn's estimator. So in their work, Stijn and co-authors propose criteria that they feel an assumption-lean causal estimand should meet. And I'd like to augment that with 2 more criteria that his proposal satisfies and 1 more that I'm not sure it satisfies. So the first criterion is that the estimand is consistent for the null under the specific null that A and Y are conditionally independent given L. So this is like the sharp null for levels of L. And this holds for his estimator, his estimand. The second is that it's consistent for a value that's greater than the null when A tends to increase Y on average across all values of L, and consistent for a value less than the null when A tends to decrease Y on average for all L. So this is to say, if there is a causal effect and it's in the same direction for all levels of covariates, the estimand should capture that directionality. And this is also satisfied by his estimand. But then the third criterion, which is a very challenging one, is that the estimand be interpretable when the relationship between A and Y is non-monotonic, or in the presence of, oh, that should be AL interactions, qualitative interactions. And it's because it's not clear to me how to interpret Stijns estimands in the presence of qualitative heterogeneity that I proposed a workflow where we first kind of assess whether heterogeneity could be present. And I'll just point out that a possible diagnostic for this was proposed in a JRSSB comment by Bouya et al. And I think that developing principled ways to incorporate tests of qualitative heterogeneity into this workflow would be one of the most interesting and important directions to pursue going forward. So now to close, I'll turn it back over to Stijn and pose some questions. So first, you've talked a lot about ensuring that your estimand is interpretable when the underlying partially linear model doesn't hold, but I'm just curious if you can be more specific about exactly how you would propose communicating with practitioners or consumers of causal research about how to interpret these estimands, and especially how to use them to make decisions or policies or develop future research questions towards decision-making and policy-making. And in particular, how would you recommend using and interpreting these weighted averages in the presence of qualitative effect heterogeneity? And with that, thanks again to Stijn and his collaborators, and here are some references.
Thank you very much.
Thank you, Betsy. Yes, please feel free to discuss the.
Yeah, thanks. That was very nice and useful. Maybe first about heterogeneity. I think what we haven't planned to do but have not done yet is more look, just like we summarize stratum-specific treatment effects as a sort of weighted average. We aim to look at variability of those effects between strata as a way of gaining insight into treatment effects heterogeneity. We are doing some work on moving away from the assumption that we have a linear relationship between exposure and outcome. And in fact, the discussion of the discussion paper gives one quick proposal, like a hint in that direction, where it's a bit like in each stratum L, we think about doing it. I mean, you could think about smoothing splines, for instance, where we model the mean outcome in that stratum on the exposure, and then we sort of average these splines across the covariate strata in a certain way. But certainly, I agree that these are important points that we should address, and I think we plan to do that in future work. Regarding communication to clinical collaborators, I mean, maybe my look at this is very pragmatic. It's not that I view the estimand as such as necessarily what we should strive for. This is more intended like in those cases where we want to relate to models, maybe because we want to, I mean, maybe we don't even have in mind looking at the effect of interventions. Maybe we would like to get a sense of the relation between exposure and outcome. I guess I would view, I mean, I would usually do the interpretation as if the model holds. I'm only trying to give a bit of a guarantee that if the model does not hold, that we still get something sensible. Maybe not as sensible as we would like it to be, but this is very much coming from the thoughts that in many cases we might not get our clinical collaborators to follow the ideal workflow in terms of coming up with an estimand. My aim is more to give them something they could use, hopefully safely, without having to relate to expert statisticians who can propose estimands and do all steps of the workflow. Although I agree, in the ideal world, one would follow the workflow. I'm just worried that we are too far away from that ideal world. And the other, maybe last point I'll make is one concern I have about the workflow is that what we would like to see ideally in, or the estimands we would ideally like to get from the data, we may often find that the data eventually do not allow us to learn it. what do we do in that case? Maybe we need to set a step back, and how does that fit in the workflow? I think that was also a bit of a motivation for this work, in trying to prevent people from being too ambitious in the estimands that they propose. But I certainly agree with many of the points you made, and that the workflow should be more integrated in what we do. Thanks. I'll maybe stop it here.
Thank you both. Okay, so then thank you, Stijn and Betsy and Oliver. I will move us on to wrapping up this talk. Just a second. Okay. Right, so once again, thank you to Stijn and Betsy for nice talks and interesting discussion. And thank you, Oliver, for answering so many questions in the Q&A. I think there's great interest in this work, so it's always exciting. Next week, we'll have a talk by Ingeborg Berenbaum from Uppsala University. So I hope you all join us for that talk next week. Thank you very much.